Welcome you all. On today's session, I will explain about how to solve the numericals on Kaplan turbines. So this numerical related to Kaplan turbine is that working under a head of 20 meter develops 11,772 kilowatt of shaft power. The outer diameter of runner is 3.5 meter and hub diameter is 1.75 meter. The guide angle at the extreme edge of the runner is 35 degree. The hydraulic and overall efficiencies of the turbines are 88% and 84% respectively. If the velocity of whirl is 0 at outlet, determine first one runner vane angle at the inlet and outlet at the extreme edge of the runner. Second one is speed of the runner. Now after reading this numerical, try to write the given data. So this numerical is related to Kaplan turbine, so that is a reaction turbine, so that is working under head of 20 meter, that is H is equals to 20 meter, and that develops 11,722 kilowatt of shaft power. The P is equals to 11,772 kilowatt. Outer diameter of runner is 3.5 meter and hub diameter is 1.75 meter. So here outer diameter is denoted by DO is equals to 3.5 meter and hub diameter D of H or D of B, that is the hub diameter is also called as boss diameter, that is 1.75 meter. The guide angle at the extreme edge of the runner is 35 degree. The guide angle at the extreme edge of the runner is 35 degree, means alpha 1 is equals to 35 degree. Hydraulic efficiency and overall efficiency is given as 88%, that is hydraulic efficiency neta H, and overall efficiency is neta O is equals to 84%. If velocity of whirl is 0 at outlet, the velocity of whirl is 0 at outlet means VU2 at exit is equals to 0. That means the alpha 2 is equals to 90 degree. So here discharge is radial. The discharge is radial at exit, alpha 2 is equals to 90 degree. That means the absolute velocity at outlet or exit V2 is equals to Vf1. So this is some conditions when velocity of the whirl is 0 at outlet. So now we have to determine the runner vane angle at inlet and outlet of the runner, that is what is the angle of beta 1 and what is the angle of beta 2. Then also calculate speed of the turbine, that is N. So these are given data. So H is equals to 20 meter, N you have to calculate, power value is given, overall efficiency is equals to 0.84, hydraulic efficiency is equals to 0.88, and outer diameter is given as 3.5 meter, boss diameter or hub diameter is 1.75 meter, alpha 1 is equals to 35 degree. So now calculate what is the beta 1 angle, beta 2 angle. So now this is velocity triangle for that given conditions. So here 1 represents the inlet velocity triangle and 2 represents outlet velocity triangle. So here the given condition is that the discharge is radial or there is no whirl velocity at exit. So here VU2 is equals to 0. So in this one here exit velocity triangle, the VU2 is equals to 0. With that the alpha 2 is equals to 90 degree and V2 is equals to Vf2. So this is exit velocity triangle, there is just right angle triangle. After referring these velocity triangles, we can find the blade angles at inlet as well as a blade angle at outlet. So here they ask to calculate the beta 1, what is the beta 1 angle and what about the beta 2 angle here. So this one is calculated by using this both inlet velocity triangle as well as outlet velocity triangles. So now overall efficiency is equals to, that is given by the ratio of power developed by the power available at the runner, that is rho g q h. So now we know the values of overall efficiency, we know the values of power developed. So here the Kaplan turbine, the water is flowing through the turbine. For that reason density of the fluid is 1000, that is the density of water. G value is equals to 9.81. The Q is unknown and H is equals to given. So by this overall efficiency formula we can find the value of discharge through the Kaplan turbine. So by the substitution of these values, the discharge is obtained as 71.35 meter cube per second. So this much of discharge occurring through the Kaplan turbine. So now the formula for discharge, the discharge is equals to area of the flow into velocity of flow. So here area of the flow is calculated by using the formula pi by 4 into d naught square minus d of b square. So here d naught represents what? Outer diameter of the runner, and d of b represents the boss diameter or hub diameter. So that represents what? The area of the flow. Area of the flow, and Vf1 represents velocity of flow. So here the Q value is known, already we calculated by using the overall efficiency formula. Then both the diameter values are known, outer diameter as well as inner diameter. So then Vf1 is unknown. By using these relations we can find the flow velocity as 9.89 meter per second. Now from inlet velocity triangle, tan alpha 1 is equals to ratio of Vf1 by Vu1. Tan alpha 1 is equals to Vf1 by Vu1. So now alpha 1 angle is given in a numerical, that is 35 degree. Tan 35 is equals to Vf1 is equals to 9.89. Then Vu1 is unknown and Vu1 is calculated by substitution of these values in a tan alpha expression. So now Vu1 is equals to 14.1 meter per second. So by using the hydraulic efficiency formula, the hydraulic efficiency is given by the ratio of Vu1 into U1 by GH. So hydraulic efficiency is given, that is 88%, that is 0.88. So V1 is calculated as a 14.1. The U1 is unknown, and in the denominator G into H, the value of G is equals to 9.81. The head maintained here it is 20. So now the U1 value is calculated, and that value is 12.24 meter per second. So now what is the runner vane angles? That is a beta 1 angle as well as a beta 2 angles. So here tan beta 1 from the inlet velocity triangle, tan beta 1 is equals to Vf1 by Vu1 minus U1. So now tan beta 1 is equals to Vf1 is equals to 9.89, and Vu1 is calculated, that is 14.1, and U1 value is 12.24. By substitution of this we get the blade angle at inlet, that is 79.35 degree. So coming to the from the exit velocity triangle, tan beta 2 is equals to Vf2 by U. So here tan beta 2 is equals to Vf2 is equals to 9.89, and U value is equals to 12.24. That means the beta 2 angle or blade angle at outlet is equals to 38.93 degree. So now I want to calculate the second part of the numerical is speed of the turbine. The speed of the turbine is calculated by using this formula. U is equals to pi d naught n by 60 and U is taken as 12.24. Then diameter, that is outer diameter, substituted here, that is 3.5, and speed is calculated, and that speed value is 66.79 rpm. So this is the method of getting the solution for the Kaplan turbines. Coming to the another problem, that is problem number 2. A Kaplan turbine develops 10 megawatt under an effective head of 8 meter. The overall efficiency is 0.86, the speed ratio is 2, and the flow ratio is 0.60. The hub diameter of the wheel is 0.35 times the outer diameter of the wheel. Find the diameter and speed of the turbine. So a Kaplan turbine, there is a reaction turbine. The power developed P is equals to 10 megawatt, and effective head H is given as 8 meter. Overall efficiency neta O is equals to 0.86. Speed ratio phi is equals to U by V1 is equals to 2, and flow ratio is given as 0.6. The hub diameter or boss diameter is 0.35 times of the outer diameter. That means dB is equals to 0.35 times of d naught. Now find what is the diameter of the wave and speed of the turbine. So these are the given data. H is given as 8 meter, N you have to calculate, P is equals to 10 megawatt, overall efficiency is equals to 0.86. What is outer diameter? And this diameter of the hub or boss is equals to 0.35 times of the diameter of runner, the external diameter of the runner. Phi is equals to 2, and flow ratio is equals to 0.6. See the solution now. From the speed ratio, that is U by square root of 2gh is equals to, the speed ratio is given as 2 and head is given as 8 meters. So by this formula, the substitution and calculation, we will get the answer for U, that is equals to 25.06 meter per second. From the flow ratio expression, so that is equals to Vf1 by square root of 2gh. So once again flow ratio is given as 0.6 and head value is given 8 meters. The Vf1, the flow velocity, is unknown, and flow velocity is calculated, and that value is Vf1 is equals to 7.52 meter per second. From overall efficiency formula, so that is equals to ratio of P by rho G QH. So here the power is given, that is given in a megawatt. The power is given in megawatt, and in terms of watt, that is 10 megawatt into convert into watt, there is a 10 into 10 to the power 6, and density of the water is equals to 1000, G is equals to 9.81, Q value is unknown, and head is given as 8 meters. So from this expression, calculate what is the discharge occurring through this Kaplan turbine, and that Q is equals to 148.16 meter cube per second. So now discharge, the formula for the discharge is equals to area of flow into velocity of flow. The area of the flow is calculated by using the formula pi by 4 into d naught square minus d of b square, that is external diameter square minus boss hub diameter square. So here the discharge is known, and pi by 4, these are some constant values, and Vf1 value is known, and d naught square minus, what about the db square or hub diameter? The hub diameter is given, that is 0.35 times of the external diameter. For that reason it is 0.35 d naught square. So now after simplification of this one, we will get the diameter, the external diameter is equals to 5.35 meter, and the diameter of the hub or boss is 0.35 times of the outer diameter, so that is equals to 1.87 meters. So now I want to calculate the speed of the turbine. The speed of the turbine is calculated by using the formula, that is U is equals to pi d naught n by 60. Here U is equals to, U value is 25.06 meter per second, and diameter, the external diameter is 5.35 meters, and speed is unknown and speed is calculated, and that speed value is 89.45 rpm. So this is a solution, this is a method of doing the solving the problems in Kaplan turbines. Thank you.